Imagine a world where your smartphone charges in minutes, an electric car travels 1,000 kilometers without stopping, and energy from the sun and wind is not lost, but carefully stored for later use. This world does not begin with factories or devices. It begins in laboratories where scientists design the materials that will power the future. Chemistry is no longer just a theoretical science. It is becoming a tool for engineering reality at the smallest scale. Instead of discovering materials by chance, researchers are now designing them with specific properties in mind. One of the most promising directions in this shift involves materials with a structure known as NASICON. Behind this complex name lies a simple and powerful idea. These materials form a rigid crystalline framework with a network of internal channels. Inside these channels, ions such as lithium or sodium move rapidly, almost like cars on a high-speed highway. The faster and more efficiently they travel, the better the battery performs. This combination of speed and stability is rare and extremely valuable for modern energy systems. What makes these materials especially important is their flexibility. NASICON is not a single compound, but an entire class of materials that can be adjusted by introducing different elements. By adding metals such as manganese, iron, chromium, or vanadium, scientists can tune how the material behaves. It can be made more reactive, more stable, or more efficient, depending on the goal. This marks a deeper shift in how science works. Materials are no longer just discovered. They are being designed. One of the most interesting developments is the use of two active metals within the same structure. When materials combine elements like manganese and chromium, they can store more energy and operate at higher voltage. In practical terms, this means longer battery life and greater efficiency. However, such systems also require new types of electrolytes that can handle these conditions. Electrolytes are becoming a key focus of innovation. Traditional liquid systems limit performance and can be unsafe. As a result, researchers are turning toward solid electrolytes and composite materials. These can prevent the formation of dendrites, microscopic structures that cause short circuits, making batteries safer and more durable. Combining different materials also opens new possibilities. By integrating phosphates with carbon or polymers, scientists can improve electrical conductivity, increase strength, and enhance compatibility between components. This allows batteries to become more powerful while remaining stable. At the same time, there is renewed interest in metal-based anodes. These can store far more energy than traditional materials, but were once considered too risky. Advances in solid electrolytes are now making them viable again. Yet even the best material is only part of the solution. A battery is a system where every component must work together. Stability between materials is just as important as their individual performance. At the smallest scale, everything matters. Particle size, structure, and contact between components determine how efficiently energy moves through the system. By controlling these details, scientists can dramatically improve performance. The future of batteries will not be defined by a single invention. It will emerge from the precise design of materials. What once seemed like chemistry is now becoming the foundation of the energy systems that will shape the future.